Hello students, hope every one of you is fine. Given that the situation is not improving so much, the current status quo might be there for the next couple of months too. So be at home, use your time wisely. So in the architecture course, we are in the memory module and we have looked at the common memory hierarchy followed by caches, then virtual memory, then the actual physical memory DRAM based, and in the DRAM module we have seen how the DRAM is physically organized into channels, DIMMs, ranks, banks, rows and columns, and how the memory controller handles such an organization, and apart from that what other jobs the memory controller has. We are further down the memory hierarchy and now we are at the secondary memory, also called storage architecture. For the next couple of classes we are going to dive into this level, and similar to the main memory and the caches, we have the actual hardware which stores the data and the control circuitry. Here too we have a disk controller and the disk technology to store the data. We are going to look at both of them. So a quick interesting point that I thought to share with you, there is something called internet minute. It is defined as the activity that is happening across the globe in 1 minute, 60 seconds. And the chart on the right side shows that across a minute, so much activity is happening, millions of users, they are generating so much of data. And there's an interesting site, I've given links, and it states that every day 2.5 quintillion bytes of data is being generated, and there's another study which says that for every 2 years the data we generate is increasing exponentially. So any common example that we can take currently is we have millions of CC cameras across, and we have millions of sensors, data points that we need to store. And even if you consider the current COVID situation, the data that's being collected for millions or billions of people across the globe, and it's still increasing, just to give a perspective. So how do we handle such huge amounts of data? This is the era of data deluge, where we have lots of data to process, handle, store, manage. There are multiple aspects to it. For example, Facebook generates almost 4 petabytes of data every day. This was nearly 5 years ago, and in the current scenario it might be even 40. There are a couple of links I'm providing here which give the underlying engineering problems to get a server setup like Facebook up and running. So as engineers, not as the end users of Facebook, I thought you would be interested in the amount of engineering that went through to get it done, and what other interesting open problems that we have currently. Another example is Google. The typical Google search can be a very good example. and Google has been handling sorting on huge amounts of data, which is again in petabytes. It's, for example, if you want to run your quick sort or any of the divide and conquer algorithms with billions and billions of data, how do we do it? Again, there are a couple of interesting problems that you can see. All such applications which deal with huge amounts of data are called big data applications, and in the current era we have big data analytics, data mining, and even the current machine learning and AI algorithms need to be trained and tested on huge amounts of data. So I guess that is good enough introduction on why we need to look at the storage architectures. Accordingly, many companies found to provide good storage solutions is a good revenue generation point. So you can find that many of the popular companies use these solutions, right from Amazon or uh, Google. It can come down to the processor companies like IBM, Intel, Micron. So let's look at the storage in more detail. Historically, there are many technologies that have been existent for the secondary memory. If you have a question why we can't use the SRAM and DRAM for storage too, it's primarily because they are very costly and they consume huge amounts of power. Also, they are volatile in nature. It means the moment you switch off your system, all the data you are working with is gone. We don't typically like such a setup for storage. So we have different technologies. One of the first ones is magnetic disk, popularly known as HDD. It has multiple such rings, and each of these is a head which will read the data that is stored on the disk, and the middle ring is called spindle. So the head on the magnetic, the tip of this head moves across the disk to read the data in and out of this disk, of the each of each disk. So we will have multiple such heads, one per each disk. Also, we have magnetic tapes. Typically, they were of huge size and they were very slow. The picture shown on the slide is quite old, probably 1960 70 time, and eventually they got shrunk in size. After that, we have again magnetic technology based floppy disks, but their capacity is quite limited, probably 2 MB to 4 MB only. Other technology is optical disk. Many of you might be aware of this already. We have CDs, DVDs, and Blu-ray with increasing capacity and price. But what's more recent and our focus in this course is flash technology. Before that, a quick comparison between the hard disk drive and solid state drive. Hard disk drive, like I already mentioned, is dependent on the magnetic direction of the underlying particle, magnetic polarity. It will be the difference in the polarity as we move from one particle to another particle is interpreted as a 1 or 0, so on and so forth. There are multiple such implementations. On the other hand, for solid state disk, we have flash memory cell. We are going to dive in. If you if we observe the random read latency to read 1 bit of data, we would typically take 6 to 8 milliseconds for hard disk, but for solid state drive it's quite fast, just a fraction of millisecond. The power usage, HDD is high and SSD is low, almost one third. If we look at the noise part, HDDs are very noisy because of the physical parts moving. SSDs are quite silent. The price, HDD is quite cheaper when compared to SSD, but this scenario is quickly changing because of technology scaling. We are able to realize SSD drives at much lower cost. When it comes to reliability, SSD drive is much more reliable than the hard disk drive. And if you look at the lifespan, hard drives are having higher lifespan than SSD. We'll also understand why this is the case. If somebody is interested, HDD is heavier than SSD. And if we look at the workloads that are ideal for HDD, they are large sequential workloads which are more or less sequential in their input and output operations. On the other hand, solid state drives are good for relatively smaller workloads, but they're quite good with their random input and output. So when we look at the flash memory, the evolution I'll quickly go through. We have read-only memory, post that we have programmable version. Then we have EPROM to erase the programmed cells. We would need to expose the entire chip to the UV light. So device scientists have come up with EEPROM, electrically erasable programmable read-only memory. We need not physically remove it. What EEPROM expects is different operating voltage for each of erase, write and read operations on the cell. So flash memory is also a EEPROM, but it slightly differs in the sense that we can write data at a much higher granularity, block level. We are going to look at the details as we go. So if you look at one particular flash memory cell, the key element is floating gate MOSFET. So we have the typical NPN MOSFET. Don't worry if you don't completely get what underlying is. This is a typical MOSFET. We have a source terminal, drain terminal, and after an oxide layer, we have the gate terminal. This is the simple MOSFET. But the floating gate MOSFET has a floating gate terminal in between, separated by the oxide layers, silicon dioxide shown in black here. Now when we apply a high voltage at the gate, electrons get trapped in the floating gate. They tunnel through the silicon dioxide insulation layer and get stored at the floating gate. Now what is the impact of this is the threshold voltage of this cell changes. Now when we apply the standard threshold voltage, if there is a current flow between the source and drain terminals, then we would say that the floating gate has no electrons trapped in it, so we would interpret it as 1. On the other hand, upon applying the gate voltage, if we do not find any current flow between the source and drain, we would say that this flash memory cell is storing a 0. So the standard nomenclature is, if the floating gate is charged, it is referred to as programmed, and we interpret it as storing 0. If there is no charge in the floating gate, we would say the flash cell is erased and interpret it as storing 1. Flash cell is non-volatile in nature, in the sense that upon trapping the electrons in the floating gate, if we remove the voltage, even if we remove the voltage at the gate terminal, the state of the cell remains same. If we look at the working, how do we read a flash memory cell? We apply the voltage at the gate and observe the current flow between the source and drain. If there is no current flow, then we would say that the cell is storing 0. If there is current flow, then we would interpret it as storing 1. How do we write to the flash memory cell? We need to apply a very high voltage at the gate terminal so that electrons get trapped in the floating gate, and we interpret such a state as writing 0. How do we erase a flash memory cell which has been already written to? We need to apply high voltage at the gate again, but in the reverse direction, so that all the electrons leave the floating gate. So here we interpret it as 1. Now, because of tunneling through the silicon dioxide layer, it undergoes a lot of stress, and over a period of usage, this layer breaks down. What it means is the floating gate will not be able to hold the electrons, and the cell can no longer be programmed or erased. So it becomes useless. Here is one technical term, endurance, which is defined as the number of times we can write or erase a cell. Because of the tunneling effect, the flash memory cell has limited endurance. When it comes to SRAM and DRAM, we have never discussed about endurance because practically they have infinite endurance. We can write and read to a SRAM cell or DRAM cell practically a very high number of times. So when it comes to the flash memory cell, this is something we need to keep in mind, and accordingly the disk controller has some job to do. There is a facility to store more than one bit of data in a flash cell. This was not the case for either SRAM or DRAM. Based on the amount of electrons that get trapped in the floating gate and observing the voltage and current, we can interpret multiple bits of data. SLC is what we have discussed so far. There is a single level, it's called single level cell. Basically, we apply the threshold voltage. If there is current flow, then we would say it's 1. If there is no current flow, it would be 0. Following that, we have multi-level cell, MLC in short, where we can apply one of the 4 possible voltages, one after another, and observe the current flow. Tri-level cell is TLC, where there are 8 possible voltage levels for programming and reading the flash cell. So a representation of such voltage levels in an SLC flash cell, the high voltage would represent a 1 and low is 0. But if you look at TLC, there are 8 possible voltage levels and each of them is interpreted as a sequence of 3 bits. As you might have already guessed, the speed of operation of a single level cell is better than multi-level cell, and which is in turn better than TLC, because we need to measure finer level finer levels of the voltages. Coming to density and cost, single level cell has the lowest density and TLC has highest density. When it comes to endurance, because we need to have a much tighter control on the number of electrons that are in the floating gate, the oxide layer undergoes even more stress. That is the reason single level cell has highest endurance when compared to MLC or TLC. So with all those in mind, let's look at a string or array arrangement of such flash memory cells. There are two possible implementation. One is called NOR flash, wherein all the drain terminals are connected to one common line called as bit line, and all the source terminals connect to the another line which is called source line, and each of the gate terminals is a word line. The other implementation is NAND flash, wherein the source and drain terminals of adjacent cells are connected, and the drain terminal of the last cell is connected to a single bit line, and the source terminal of the first cell is connected to the single source line. And just like NOR flash, each individual gate terminal will form the word line. So typical sizes of such strings of memory cells is 32 to 64. It means that a string of 64 cells can store 64 bits of data. If we are considering SLC, it means that 8 bytes of data. Such strings, when they are connected or extended, let's say in the x direction, form an array. We are going to look at the array arrangement a little more in detail. Before that, a quick comparison between the NOR flash and NAND flash. Because of the underlying arrangement difference, both have pros and cons. Let's look at them. NAND flash tends to be having higher density than NOR flash. The cost of NAND flash is lower, means it is cheaper than NOR flash. The read speed of NOR is better than NAND, but the write and erase speeds of NAND flash are much better than NOR flash. Power wise, there is a certain trade-off, but if you look at the last column, the preferred application, NAND flash is preferred for data storage because of its lower cost and higher density or higher capacity, and NOR flash is typically used for code execution and storage. One quick application area is the NAND flash is used in our regular day-to-day systems, laptops, desktops, servers, etc. NOR flash is typically preferred for embedded systems or IoT devices. We will dive further into NAND flash, and we are not going to look at the NOR flash beyond this point. In the next recording, we are going to look at the architecture of such NAND flash in detail. I'll pause for now. Thank you.